So now I want to discuss person time. The interesting thing is when we're calculating a rate, say like incidence rate, and we're looking at the number of new cases, generally we think about it as we have the sample and how many individuals in that sample came down with the condition. Now, if we do that at one time point, that's pretty simple. We can just divide the number of new cases by the total number of individuals exposed, and then we get this incidence rate. However, if we collected data on individuals over time, like say every year I check people, say people entered a clinic, they came once a year for 3 years, and I assessed them for whatever disease there is, and I calculated this. I did the same calculation and I don't take account of for the fact that they came in three different times, I would get an inaccurate estimation of the incidence. So to generally I get an overinflation of the incidence. To counter that, we account for the number of time points the individual was seen or visited the clinic or whatever, or measured. And we do this using something known as person time. So person time is an individual's contribution in time units to the calculation of a rate. Okay, so how many times that they come in to be measured. If an individual is only measured once, they only contribute one person unit of time each. So here's an example. If I calculated the incidence of type 2 diabetes in a year and I surveyed 1,000 people, each person contributes only one person year to the calculation of the incidence. In that case, we have 1,000 person years. Okay, so each 1,000 people, each individual is measured once. Each individual contributes a year. So we have 1,000 person years. Now, if we find that there are 10 new cases of type 2 diabetes, the incidence of type 2 diabetes, and we wanted to know what it is per 10,000, we do 10 divided by 1,000 and multiply that by 10,000, so we get a rate per 10,000. So we'd have 100 per 10,000. So it means 100 individuals out of 10,000 came down with type 2 diabetes or new cases of type 2 diabetes. In this case, though, this is actually an incidence proportion because it's the proportion of those 1,000 who who or became afflicted with type 2 diabetes. So this is where the danger is because if we measure people, if there's 1,000 individuals, but we measure them three times, say, for instance, it's not the same. It's no longer an incidence proportion, right? Unless we want, if we that's what we wanted to know, then of course we could calculate that instead or report it as such. If we had measured individuals more than once, we have to account for that measurement with each person contributing 1 unit of time for each measurement occasion. So in this case, if 1,000 people are surveyed three times, once per year for 3 years, each person contributes 3 person years. So 1 person year per year, assuming no missing data. We'll talk about the issue of missing data later. So for the total of 3 times 1,000 or 3,000 person years. Okay. Since there were 1,000 individuals, we saw them three times. It's 3,000 person years. If 25 new cases of type 2 diabetes are identified over the 3 year period, again, so they're going for the regular checkups, or they're visiting their clinic, or somebody's doing a study and they're seen three times, the incidence rate per 1,000. Again, so I'm always changing this rate base here. It's interesting. I was talking to students about this the other day. You can make a condition appear more profound by changing its rate base, right? Because you're going to multiply the rate by whatever the base is. So we'll multiply it by 1,000 here, so move it three spaces to the right, three decimal places to the right, and all of a sudden you'll get a much more profound looking value. But what if we did it per 10,000? This would be 83.33, right? Per 10,000. It just makes it look more profound, good for communication, and whatever your intent is. So here in our case, the incidence rate is 25 divided by 3,000 times 1,000, and we get 8.33 per 1,000. 8.33 per 1,000. That's basically 25 divided by 3. So an alternative would be just to calculate your rate and then divide it by the number of times an individual is measured. So you get divided by 3 and we get the same thing before we multiply it by 1,000. Yeah. So if we didn't include person time, this is what would have happened instead. So we have 25 out of 1,000. We'd have 25 per 1,000. So you see, this makes it look a lot worse than it is. It's false. It's not correct. I mean, you could say yes, 25 out of the 1,000 acquired type 2 diabetes, but it happened over this 3-year period. So you have to account for that time. So it wasn't like all at once, right? It wasn't all at once. Okay. Sometimes there's missing data, and when there are missing data, we have to account for that. So we can't just say, okay, there's 1,000 people multiplied times 3. But we have to see what pattern of missing data there is. Unfortunately, anytime we do a prospective study or repeated measures design study, people will go missing. Either they'll drop out, they'll be lost to follow-up, or they'll miss a time point for some reason or another. So if we have a sample of 25 adults and are interested in calculating the incidence rate for HIV over a 3-year period, and here's what our data looks like. X represents present, dot represents absent. It's your universal symbol for missing data, and we present those in table 1. So here's table 1. We have 3 years, so we have these 25 folks. You can see that first year everybody was there. There's no missing data. The second year there is some data missing, right? 1, 2, 3, 4 individuals missed the second year, and then 1, 2, 3, 4, 5, 6 individuals missed the third year. So if all 12 individuals, if 12 individuals out of this 25 became HIV positive, confirmed by testing, and all individuals remain in the sample across all 3 years, what is the incidence rate? So in the ideal world, you'd have, well, there's 25 of them that were measured 3 times, measured 3 times, like once a year over 3 years. So each one contributed one person a year per measure. There was 25 individuals. So the first year, we had 25 person years. The second year, we had 25 person years. In the third year, we had 25 person years for a total of 75 person years. So we divide 12 by 75 and multiply it by 1,000. We get 160 per 1,000. That's my incidence rate for HIV. But that's not always going to be the case. And that's highly unlikely to be the case. You're going to have missing data. As I mentioned, that it happens for a variety of reasons. So we can look at the table here and we would recalculate the incidence rate, but we're going to account for the missing data. So the first year, we had a contribution of 25 person years. So each person contributed one person year, and all 25 were there. The second year, we had 4 people missing. So 21 out of those 25 contributed person years. So we have 21 person years. And the third year, 6 individuals were missing. So we had 19 person years contributed. So if we add these up together, we get 25, that's 46, 56, 65. 65 is our denominator. So 12 divided by 65 multiplied by 1,000, we get 184.165 per, well, I just rounded it up, per 1,000. So this is rounding, and this is not rounding. Okay. Big difference in our incidence. In this case, where we looked at the the incidence rate where we had no missing data, we had 160 per 1,000 accounting for missing data. It actually increases it. So in a sense, we had a lower estimate when we didn't account for missing data. All right, a couple other things to talk about. Let's talk about population prevalence. So prevalence is the number of existing cases, right? It's just the number of existing cases. Prevalence includes both new cases, incidents, and existing cases. So here's just a very basic, and again, this is very, very basic stuff, a very basic calculation of prevalence. An example, and this is looks like it's a point prevalence. A review of patients reported to the tuberculosis registry of Midville revealed that as of July 1, 2020, there were 35 cases of tuberculosis not yet completing therapy. The most recent population estimate of Midville was 57,763. What is the prevalence of TB, tuberculosis, per 10,000 in Midville on July 1, 2020? So this is a point prevalence because it's one point in time. So we have prevalence is 35 because there were 35 cases, right? Out of the population of 57,763. Then we multiply it by 10,000, we get 6.059 per 10,000. That's how many cases exist. Out of every 10,000, there are 6.059. Attack rate is used when we have an outbreak of some issue, whatever. So we talk about attack rate as being it's like incidence, but it's localized to a specific time point. Things are happening rapidly. There's some kind of a common source outbreak, maybe food poisoning or something like that, right? So it's the number of new cases from among a set number of individuals. So these are whoever were exposed. 600 students, here's my example, 600 students living in the high-rise dorm dined at the tree trunk cafeteria last Friday afternoon. Of the 600, 158 Benny's meatloaf surprise for lunch. Yummy. Of those 150, 93 came down with gastroenteritis, placing a great strain on the university's septic system. What is the attack rate for gastroenteritis among those eating Benny's meatloaf surprise? Okay, so our attack rate was 93 divided by 150 because we're 150 exposed. And of those 150, 93 came down with gastroenteritis. So that's 62%, right? 0.62 or 62%. Secondary attack rate, sometimes people who were afflicted with the condition expose other individuals to the condition, and then there's this propagation of the pathogen rather than from there being a common source. Now it's propagated transmission. So we could have transmission that's either common source or propagated. Common source transmission is that which occurs, well, we said that the attack rate after somebody ate some tainted food, then those individuals got sick. But if other people got sick who were not exposed initially, but they were exposed to individuals who were cases, then we have propagated transmission. So this is known as secondary attack rate. So it's the number of new cases among contacts. So although not eating Benny's meatloaf surprise, 37 individuals living with primary cases came down with the same illness. For your information, each primary case lived with two other individuals. What is the secondary attack rate? So let's do this in steps. Step number one, identify the number of primary cases. So there were 93. All right, cool. Step number two, identify the total exposed. So that the 93 cases lived in households of three. So there's three, including the primary case. So each household included 279 individuals. So that's basically the people who are exposed. However, those 93 of those 279, the primary cases, cannot be reinfected, so they are ineligible for reinfection. So we have to remove them from there. I mean, you can just do this by multiplying by 2, but I'm showing this in a step-by-step fashion. So we get 186 individuals, all right? So the secondary attack rate is 37 because we have 37 new cases, right? From those, again, we cannot include those who were originally ill because they can't become ill again because they're already ill. So we have 37 divided by 93 times 2, which is 186, right? Because we remove this 93. So we get 0.199 or essentially 20%. So that's my secondary attack rate. Although the primary attack rate was a lot larger, the secondary attack rate is still pretty significant. That's all I'm going to talk about today. All right, thank you, everybody. Bye.